Okay, hi, welcome back. Okay, so yeah, if you all realize, right, I added a nice animation in front, right? That'll be the logo for all my physics videos from now on. Okay, anyway, today in class for sound chapter 1, we went through the idea of the tuning fork, okay, how it causes compression and refraction in air, and we went through speed and energy transfer in solid liquid vacuum. I think I missed out a few parts, okay, so let me do it here. Okay, after which, right, I will try to finish the rest of these notes. Okay, questions excluded, questions we'll still discuss in class. Okay, so let me get on here. Alright, since solid is dense, particles are okay. Basically I'm going to read out here first. Okay, am I even recording? Yeah, okay, I'm recording. Okay, since solid is dense, particles are able to transfer energy at a faster rate. However, the speed dissipation is higher. I mean, the energy dissipation is higher. Okay, now let me zoom in. Now, particles are able to transfer energy at a faster rate. Okay, I linked this to the idea of Ke. So, assuming that the particles are they only possess Ke at this point. Okay, if they can transfer energy at a faster rate, that will also mean that the Ke is probably higher. So yeah, I need y'all to add this point. Okay, speed of sound is fastest in solid. Okay, and the speed of sound in liquid, okay, is slower compared to when in solid. Alright, yeah, then I also talk about this, about, hey, why is my screw not working? Okay, then I also, okay, and of course in vacuum, since sound can't travel, okay, there's no speed to compare. Okay, now then I also talk about this, the energy dissipation due to unnecessary motion. Okay, and I said over here, the closer they are, the lesser the energy dissipation. But over here, when we deal with solid, the more packed they are, right, the higher the dissipation of energy. Okay, I want to clear up this confusion. Okay, I know I explained this in class and I think everyone got it with this diagram. Okay, it's basically scenario A versus scenario B. A person that is far away and a person that is near. Okay, you need less energy to convey the same message at the same volume to a person that is nearer as compared to the person that is further. Okay, I'm quite sure this is quite a common sense thing, right? But maybe it is not so right to use the word energy dissipation here, so I need y'all to cancel this. Okay, and I'm going to give you a new statement. Okay, so yeah, sorry about that. So let's see, let me erase this part. Okay, what I was trying to say, right, was that energy is transferred via vibration between each particle. Okay, and maybe less energy. Hey, what happened? Did you just go crazy? Okay, let me close this and on again. Okay, it's back. Okay, so less energy is needed to project a sound wave of same volume in A than B. Okay, of course the A refers to here and the B refers to this. Okay, so less energy is needed to project a sound wave of same volume when a person is nearer, okay, that is in A, than when a person is further away from it, that is in B. Okay, now let's keep the term energy dissipation solely for the purpose when we deal with solid, liquid, vacuum, and of course gas, which is gas is quite something that we have been dealing with all along. Okay, so I think that's fine. Okay, so at this point, please don't, yeah, I know some of y'all want to skip, right? Okay, I'm gonna ask y'all some questions in class, like what are the random things I said. Yeah, in the video. Okay, so look out for it. Okay, I'm going to test you all to see who watched the video. Okay, so check for understanding 1. These are the answers. Okay, so I think I went through page 4, should be fine. Okay, let's carry on with the rest of the page. Okay, I'm going to go through this in class. These are questions that I want you all to try, so please go and try page 5. Okay, for this, right, I want you all to explain in terms of in series of compression and rarefaction. Okay, now page 6, I want you all to think about it also, so I'm not going to go through. I'll go through in class. Okay, now page 7 is the interesting one. Okay, after I finish page 7, right, I basically kind of almost finish the whole of sound. Okay, just the application I haven't finished. Okay, so let's try to finish up page 7. Okay, now I want you all to note this idea, okay, that the energy is actually directly proportional to the amplitude square. Okay, this is a mathematical relation for waves, and in particularly not only for sound wave but also for EM waves, for light waves, for water ripples, for man-made waves. This is true that we see an association of energy and the amplitude square. Okay, so this is the idea. Energy is directly proportional to the amplitude square. Okay, now I want you to then think about this. Okay, I'm going to draw a displacement time graph first. Okay, if you want to fill in all the axes, you can. Okay, basically I'm going to draw this few graph. Okay, so I'm going to draw a displacement time, displacement distance, and a pressure time. Okay, basically what we did in the chapter 13 or 12 on the chapter on waves. Okay, I think I went through this quite in detail. Okay, so first thing first, let's draw this down, okay, to the point of compression and rarefaction. Okay, and let's not mark anything yet. Okay, now let me do a hypothesis, okay, with a thought experiment. Okay, so a thought experiment. Now the particles at the point of compression, right, it's going to be so compressed, right? Do you think it's able to transfer any energy at this point? Okay, imagine, right, you are here, okay, and one person comes over to you, bangs you to so that it pushes you to the left. Okay, it pushes you to the left, but at the same time someone is going to push you to the right also. Okay, at the end, what are you going to become? Are you going to move to the left or to the right, or remain stationary? Okay, if these two are of equal amount of force, we know in Newtonian mechanics that this particle here is going to remain stationary. Okay, or at least it's going to vibrate about its position. Okay, it's not going to move much. Okay, so in fact it's going to stay here. So for a particle at the compression point, right, it's going to stay there also. Okay, if it's going to stay here, right, it is actually not able to transfer its energy from one point to another. It's just going to stay there. It's not going to transfer its energy around. Okay, so at this point we expect there to be no energy transfer. If there is no energy transfer, right, zero E transfer at compression, which is written as C, then can you relate to this now? If energy is directly proportional to A square, okay, E equals to KA square, right, where K is a constant, right, and we say that there is zero energy transfer, right, then K is a constant, a non-zero constant, right, a non-zero constant. Then what does that make of A? What do you think is the value of A? Okay, anyone would know lah. A would then be 0. So at compression point, displacement is 0 because amplitude is 0. Okay, because at compression point there is no transfer of energy. Okay, then how about rarefaction? Okay, do you think there's transfer of energy? Now, if this analogy of particle, right, same, okay, this is the rarefaction point. Okay, things are going to spread out away from it so far that it's not going to transfer energy to anyone. It's unable to do so. It can't travel that far to transfer energy, right? So if it can't transfer energy, same argument. Okay, I'm gonna write here, okay, same argument. Okay, same argument, so therefore there'll be no amplitude, okay, because no energy transfer, no amplitude. Okay, now I need you all to do this, okay. For compression, right, that means particles here, they are moving to the left, correct? For rarefaction, that means the particle here are moving to the right, and so forth, right? Okay, now I want you all to write this. Take right as positive, okay. If you want to challenge me, you can do so, no problem, okay. Just write take left as positive, but for this case I'm going to take right as positive, okay. There's not much of an issue here, really. If you want to take left, go ahead, it's just a vector thing, okay. So I take right as positive, so all the particles that are moving right, okay, I'm going to highlight them in green, okay. All the particles that are moving right, they should be positive. All the particles moving left, this region here, they should be negative, okay. So at the end of the day, what you get is a sinusoidal curve, okay. Sorry, the graph is not very nice, but I'm sure you can draw better. Okay, because we take right as positive, so this is the green region, right? These are the green region, correct? They are the part where it's moving to the right, and these are the blue region, the part where it's moving to the left, okay. Now I know the graph seems that the particle seems to show the particle is moving up and down, but please know this is an idea of positive and negative. Displacement is a vector unit, remember. So the positive only tells of a positive direction, and negative tells of a negative direction. Now we already define right as positive, so when it's positive, it's actually moving to the right. When it's negative, it's moving to the left, okay. And because this is a distance time graph, you know, this is actually considered as one period, okay, t. Now you can't tell the wavelength from a time axis, okay. You can only tell wavelength from a distance axis. Okay, the graph is pretty much the same. Okay, so I'm going to draw it in black again. We're still taking right as positive, okay. So this is the green region still, and this is the blue region, right? Yeah, and same thing, this is the wavelength. And then comes the interesting one, okay, the pressure time curve. Now at compression, when everything, right, collides onto the particle, all the other particles around it starts colliding to it, do you think the pressure at that point, is it a maximum or minimum? Should be a maximum, right? CR, right, should be maximum. So the pressure, it should be maximum. And at rarefaction, when everyone starts leaving you, okay, the pressure should be very low, right? Very high and very low. Okay, so these are the corresponding points, okay. Now then we'll start plotting the curve. It should look something like this. Okay, now then one last question before we end this video, okay. And the question, yeah, pressure, right, is it a vector unit or a scalar unit? Okay, I want you to think about this. We can discuss in class. This is a positive and this is a negative, okay. If, okay, so I'm going to write here, if pressure is vector, then what does positive mean? If the pressure, right, is scalar, does that mean that negative pressure? What is negative pressure? I only heard of positive pressure, right? What is negative pressure? Okay, so yeah, I hope you all understand this graph. Okay, if you need to copy the whole thing one shot, okay, you can pause the video here. If not, let me move down and let me bring up this one. You all should be able to do, no problem. Let me bring your attention to this. Okay, now double the loudness, double the pitch. Okay, let me give you the relation here. I'll teach in the next video on sound 2. Okay, this is We are still at sound 1, okay? How come I can't bring this up? Yeah, we are still at sound 1, okay? I will go through in detail about pitch and loudness in sound 2, but let me just give you all the relation first, okay? Loudness is linked to amplitude. Okay, so the greater the loudness, the greater the amplitude. Now, so I guess if you are intuitive enough, you should be able to guess pitch is linked to frequency. So the greater the pitch, okay, same thing, same relation, the greater the frequency. With this, I think you all should be able to do this question here, part 1 and part 2. There shouldn't be any problem, okay? And yeah, I think I'm done here. Okay, so I'll end sound 1 here. Okay, next video will be on sound 2. Okay, thanks for watching. Bye.